Hi all, and welcome to the Medical AI Lab group session. Today I'm delighted that we have Vish Rao presenting to us on Decoder Denoising Pretraining for Semantic Segmentation, which is a recent work from Google Research. So without further ado, Vish, take it away.
Sure. So before getting into the actual aspects of this paper, I want to touch on the problem definition. So in semantic segmentation, we assign a classification label to every single pixel within an image. And what this means is that the ground truth labels are very expensive, time-consuming, and sometimes inaccurate to curate because there are labels that are needed for every single pixel of the image. And as a result, it is difficult to obtain large data sets for supervised learning. And as a result of this, we traditionally use a pre-trained encoder and a randomly initialized decoder for semantic segmentation. So for semantic segmentation, we normally use an encoder-decoder network with the encoder necessary to extract the latent features within the image and the decoder necessary to bring back the resolution of the original image. So in this case, to say when we're dealing with small data sets, it's better to use a pre-trained encoder. And the hypothesis of this paper is that using a randomly initialized decoder is suboptimal because for the same reason why using a randomly initialized encoder is suboptimal. So in this paper, they hypothesized that using a pre-trained decoder on the denoising task will actually help semantic segmentation performance. So now I want to go through the overall approach proposed by this paper, and then I'll delve into each of these steps individually. So firstly, they propose a supervised pre-training of the encoder. So this is the standard approach that's currently used in the literature where you have the encoder, which is pre-trained on, for example, you'll have a resident 50 backbone pre-trained for ImageNet classification. So this is a pretty standard thing that's used in the literature. And yeah, so that's their approach for the encoder. And then for the decoder, they pre-train the decoder on the task of denoising. So I'll get more into denoising later on, but denoising is basically where we add some sort of Gaussian noise to the image, and then we train the model to be able to predict the original image given this noisy image. So the idea is that they're going to pre-train the decoder portion of the model using noisy images and optimize to minimize the reconstruction error of the original image. And then finally, using both of these aspects together, where we have the pre-trained encoder and decoder, then there will be fine-tuning on the actual fine-tuning data set available. And then one other thing I wanted to note is that the main metric that they use throughout this paper is mean IOU. And this is a pretty common metric used in segmentation tasks. And it basically is the ratio, say we have two segmentation masks, then it is the ratio of the intersection between these masks to the actual union of these masks. So next, I want to go through the overall process of denoising. So say we start out with an original image called X. So we can add some sort of Gaussian noise to this image given by epsilon here with a mean of 0 and some set standard deviation. And we have a noisy image, X bar. So basically in denoising, we will be passing this noisy image into the autoencoder. So I should note that F here represents the encoder and G represents the decoder, where the theta represents the parameters of the encoder and phi represents the parameters of the decoder. So as we can see, we pass our noisy image into both the encoder and then the decoder, and then we're actually minimizing the mean squared error between that and the original image. So that means that the idea of this approach would be to try and reconstruct the original image from the noisy image. And one thing that's important to note here is that in the standard denoising approach, we optimize for both phi and theta. So for both the parameters of the encoder and the decoder portions of the model. And you'll see that they actually did not do this in this paper, but this is a standard approach that's used in denoising. So another thing that I want to quickly touch on before getting into this paper's specific implementation is the idea of a diffusion model. So in this case of denoising, instead of predicting the actual original image without the noise, they're actually predicting the noise vector directly. So as you can see in this objective function, we're finding the error between the output and epsilon, which I mentioned is a noise with the mean of 0 and a set standard deviation. So in this sort of diffusion model, we're predicting directly for that. And they found that when using this in their denoising pre-training, they were able to achieve higher performance on the downstream segmentation task. So in that sense, this is the specific approach that they went with during denoising. So they found that like pre-training using this denoising task could work for both. They could apply to both the encoder and the decoder, which is standard in denoising. But they found that denoising by itself performs behind standard supervised pre-training when there's enough fine-tuning data. So this table here shows this pretty well. So we can see that, first of all, when they have a large amount of fine-tuning data, so 100% or 25% of the total fine-tuning data available, the supervised approach where the encoder is pre-trained on, sorry, the encoder is pre-trained on using a supervised approach. So for example, as I mentioned, Resonant 50 on ImageNet, we can see that it performs better than the denoising pre-training for both the encoder and the decoder. But we find that when there's a far fewer portion of the fine-tuning data available, the denoising pre-training actually performs better than the supervised approach. So that's something interesting that they found, and they're going to go ahead and combine both approaches to achieve the best of both worlds. So next, I finally reached their objective function formulation for decoder denoising pre-training. So firstly, I should note that they're only optimizing for the 5 parameters, which I mentioned are the parameters for the decoder. So this means that they're freezing the encoder, which is very important. And then next, they went with this scaled additive noise approach. So as we can see, as opposed to just passing in the image with the added noise, they're actually scaling both relative to one another. And this is something that's commonly used in the denoising literature, which they drew upon, and they found that this improved performance. So they went with this when passing in their image into their encoder decoder formulation. And then I should also note is that they're using the diffusion formulation of this problem where they're predicting the noise vector. So this is their overall objective function for pre-training the decoder. So I should note that they did draw upon a lot of things from the denoising literature for this formulation, and they did try things from that literature that did not work. So this gamma parameter that I mentioned earlier, which is how you scale the image versus the noise. So they tried a variable noise schedule. They tried conditioning on it, which means passing it into the model as an additional input. And then finally, they tried weighing different levels of gamma in the actual loss function for each different level of gamma used. And they found that all of these were actually unnecessary since a fixed gamma works the best. So then before getting into their results, I want to go over a bit of their implementation details. So they used a transunit model. So UNet is a pretty standard model used in semantic segmentation, and it's good because it basically consists of an encoder and a decoder, with the encoder extracting the features and the decoder reconstructing the original image with skip concatenations, which allow you to preserve the resolution of the original image. So the difference between this transunit and the original unit is that the encoded features are passed through a 12-layer transformer and then a 12-layer vision transformer, and then back to the decoder portion of the network. So, and I should also note that in their approach, they incorporated data augmentation. So they had random flips and random props when training their model. So next, when we get to the results, they are pretty self-explanatory, but impressive nevertheless. So we can see that, first of all, no pre-training works worse than these other pre-training options, which is as expected. And then we find that when using large amounts of the data available for fine-tuning, that the supervised pre-training does perform well. And the denoising pre-training, on the other end, performs better than supervised pre-training using a smaller subset of images. But then we find that when we combine both, so when we have the supervised pre-training for the encoder and then the decoder denoising pre-training, we find that this achieves better performance across all amounts of fine-tuning data that they had, which is pretty impressive. So that was for the cityscapes dataset, and they tried this again on a different dataset with perhaps more stark differences in between the different pre-training settings. So we can see that supervised pre-training really struggles when you're using a smaller subset of the training images available for fine-tuning. But then decoder denoising pre-training, which combines both approaches, is able to perform well across the board. So, and then we can also see, like I mentioned earlier, that they used a transunit model, which is a relatively more complex variant of the unit model. But they also found that this performance improvement is generalizable to simpler models. So they tried this with a simple unit model, which just uses pre-trained resonant 50 backbone. And they found that this decoder denoising pre-training approach also improved performance there. And then finally, they found that this denoising approach is scalable. So on the y-axis of this graph here, we basically see the number of epochs that the denoiser is being pre-trained. And we can see that there's a linear association between how much we pre-train our denoiser and the mean IOU on the downstream segmentation task. So what this is telling us is that this isn't like a hyperparameter that we normally would have to control for, where, oh, if we pre-train our denoiser too much, we'll get diminishing returns, or it'll perform worse. So this is something that is instead scalable and is only really limited by the amount of computational tools that you have to pre-train your denoiser. So I believe that the takeaways from this paper are twofold. So firstly, I thought that it was really interesting that probabilistic models used in image denoising can learn relevant image characteristics that could be used for semantic segmentation. And then perhaps more importantly, that decoder denoising pre-training represents a very simple yet powerful method that can improve semantic segmentation performance. And this improvement is especially useful when we lack abundant fine-tuning data, which is often the case for semantic segmentation tasks. So that was it. Please let me know if you have any questions.
Awesome. Thanks a lot, Vish. Thanks for the excellent presentation.